Jesse Berezovsky is a professor of physics at Case Western Reserve University. He earned his PhD from UC Santa Barbara in 2007 and went on to research at Harvard before building his own lab at Case Western, where he designed systems aimed at enabling scalable room temperature quantum technology. Beyond his quantum work, he developed a statistical mechanics approach to music theory, treating music itself as a kind of phase transition, and built Viviscore.ai, a generative music platform based on that theory. He also created CatLand, an online tutorial that walks through quantum mechanics from fundamental waves all the way to the classical reality we experience. My first question for you, Jesse, is how were you in college? What were your dreams and ambitions then?
When I went to college at the University of Minnesota, where I grew up, and I always knew I liked building things. I like solving puzzles. And so my question was like, where am I going to find a place where I can do that? I kind of maybe physics, maybe engineering, but I quickly fell into working in a physics lab and I just loved it. As much time as possible in the lab.
Yeah, take me back to that first moment in physics that truly grabbed your attention. Was it a book? Was it a question? Was it a problem?
Always interesting to learn about the theory aspects of physics, and I had some talent for it, but I got the opportunity to work in a lab starting in my freshman year. And I just would just hang out in there and try to learn every single piece of equipment and go through every drawer, learn all the different stuff in every drawer and where everything was and how it all fit together. And so that was really what I loved. And then what was really exciting is when I found out that this underlying theory of reality, quantum mechanics, was now at a place where we have the technology to start actually making useful things out of some of the weirdest aspects of what underlies our reality.
Use the word weird. Is it weird fundamentally, or is it weird because it doesn't conform to our Newtonian perspective of reality? And is there any reason why it should appeal to us specifically?
Well, right. It's weird because it's non-intuitive. I mean, it really says like, okay, we don't really know what underlies everything, but it's very different than what you would think.
Yeah, definitely. And I kind of want to pull back to your music world for just a moment. The viola, why specifically the viola? Most kids would pick up something like a violin, and that's an instrument of personality.
That's right. Well, there's a story behind it, which is that when I was maybe 5 years old, my parents took me to a thing where you kids could try out all the different instruments and see what they like. And I tried out all the instruments, and then I decided that I liked the violin and wanted to play the violin. And the person leading this class told my parents, I think he's a better fit for the viola. And so they signed me up for viola lessons, and that's what I've played ever since.
Interesting. Einstein said he'd be a musician if he wasn't a physicist. And he credited the violin to a lot of his greatest achievements in thought. And often when he would cite, even in some of his writings, that when he would have blocks and when he was trying to understand general relativity, he would go and play the violin, and that would open his mind to further thought. You're a violist who built the first physics-based theory of music. Is that a coincidence of the trade, or is there something deeper at play here?
Well, there's definitely like a history of physicists also being musicians and studying music. Going back to Helmholtz, for example, Huygens, or some of the famous names from the history of physics, who also studied music, different kinds of scales and tuning systems and things like that. I guess you could even say Pythagoras, had his mathematics and music. And so there's always this sort of fascination of the connections between these fields. And in terms of actually playing music, I think it's very good to do a variety of things, to exercise your brain in different ways and not get stuck in one rut that you just follow all the time.
I know to you it might seem intuitive, but for someone on the outside, it seems counterintuitive. They seem like they're disciplines at opposite ends of the spectrum. You put your science, technology, engineering, and mathematics, and you put your arts completely at the other end. And I wonder, what does the saying, sometimes science is more art than science, mean to you?
It's an interesting question. Like, why do we even do science? And I feel like that's a question that comes up a lot now in my mind with AI uh, coming into the scene and starting to prove mathematical theorems and things like that. You start to ask, well, why were we even doing this in the first place? Is it particularly useful if an AI system can come in and prove a million theorems or something? Or for that matter, if an AI system can come in and write 1,000 more Beethoven symphonies? Do we want that? Do we need that? Why did we want them in the first place? I think there's a human aspect, both certainly in arts, but also in science. The discoveries, we like learning about discoveries of famous physicists, about Einstein or Newton or Feynman or whoever. But like part of it is that it was created by a person. And that makes us even more fascinated by this sort of human endeavor of how we've been able to build these things up. That's what I feel like the connection between arts and science, in terms of the art of science, is that when I'm choosing what experiment to do, at least for myself, I'm not just thinking like, what will advance human knowledge the most? What experiment can I
Mm.
do that will solve most efficiently an outstanding problem that might be useful to know the answer to? I'm thinking like, what's going to spark my imagination or spark other people's imagination and just make people say, wow, that's really interesting. And so that's sort of an artistic aspect, is that you're thinking about how to spark something in people's minds.
Yeah, but what I find interesting is that you mentioned that music is a product of human ingenuity, and I want to extrapolate on that because I wonder if music is a language of the universe. If you were to teleport me into a different planetary system, and I'm in the mall of some alien species, and I hear noise coming out of the speakerphone, would I intuitively be able to discern what noise is music specifically? And what I mean by that is that you're looking at music as being something that's just like an underlying product of communication. Like you can separate civilizations across oceans, but they'll still conform to an axiomatic structure for music. And I guess, is this something that we've discovered or is this something that we've invented?
I think that, like, if you were to take humans and start over again, go back in time, rewind the clock, play it forward again, I think we would wind up with music that's similar to what we have. In other words, I think that it's not just random chance that we decided to make music the way we do, but there's actually underlying fundamental reasons. But I think those reasons are relying on actual human brains. And so alien brains might not be the same.
Hmm.
And I say that because there's a lot of studies done how different animals perceive rhythm, and other aspects of music as well. But in particular, rhythm is interesting because very few animals can keep a beat like we can. For example, monkeys can't, but there's a number of types of birds that can. It's not just like higher order intelligence or something organizes sounds the way we do. It's something specific about the way our brains work and how we process sounds and how we tease out patterns in sounds and things like that, that leads to the reason why we all kind of make music in the same general way.
Interesting. So I guess what you're saying is that if I was on an alien planet, I would not be able to tell a difference between what's communication and what's sounds and what's actually considered music on that planet. I might not understand it, but I'd somehow be able to feel just like consonants and vowels are a product of language, regardless of what language is spoken. Akin to that analogy, I would say.
Yeah, I think it would have to be a situation where their brains worked in a similar way to ours for that to
Mm.
happen. And I don't know that it would have to be that way. I think
Interesting.
you know I think you could tell the difference between sounds that were being used for communication versus meaningless sounds, because there has to be some structure and some information conveyed, and you can analyze that sort of thing. But whether they would structure it the same way, I think that depends on our human psychology.
Very interesting. I want to kind of dive into quantum mechanics for just a moment. So, do you feel like we have any predictive power of once we cross that Rubicon of quantum supremacy, what a world might look like?
It's very hard to predict. Um, it's about the future. But I always look back to analogies with, when we're developing our computers we have today, people did not know what was coming. You could find all these quotes from famous people from the 1960s or something where they just did not see what was coming with computers. You think you see, but usually it turns out to be radically different. Still, hopefully, even more exciting than when we think. You never know. But it's hard to predict because right now the technology is so early that it's hard for us to imagine it not being so hard anymore. In the early
Mm.
days of computers, it was like, okay, maybe we'll get the weight of a computer down to 1 ton. It was hard to imagine, oh, well, they'll have these things in their pockets. People would say, you'll never have a quantum computer in your pocket because it's just too hard. But that's the way things are now.
Yeah, I have so many questions on that. Before I dive into this, specifically quantum computing, you mentioned how classical computers were interpreted in the early days. I want to talk about Moore's law and the diminishing returns that come with innovation in a specific vertical. So it seemed clear to us that with the integrated circuit, we pack more transistors and it's faster. And Moore's law is kind of held up for some time, but eventually you kind of get diminishing returns where the amount of energy you put into R&D, the output is just kind of getting less and less. And now we're hitting this world of quantum tunneling and we're hitting the nanoscale and our calculations are becoming more flawed. And this is where the aspect of art falls into the world of science, where You kind of have a discovery, the integrated circuit, and then it's all about engineering, optimizing, and just getting the most out of that concept. But to take that next leap forward, you need someone with an artistic mind, something novel, something completely, it almost sounds crazy until it's proven that it works. And I guess this is where your field of expertise falls into place in quantum computing. Talk to me about that issue with why classical computers, I wouldn't say quantum computers are going to replace classical computers, but in terms of that next leap forward, it looks like we're reaching some sort of threshold with our ability to compute with the classical structure.
Yeah. There's a lot of things. Could be quantum computers. There's other sorts of emerging technologies that could open up new ways of processing information. Things like neuromorphic computing that just use a different paradigm to process the information. And it's absolutely right that we do not know what the thing is going to be. Like you can look at today's quantum computers, for
Neuromorphic?
example. Yeah, it's basically mimicking the way we think the brain processes information through some collection of these interconnected nodes, and it's not like a perfectly programmed series of logic gates like in a classical computer, but it can be trained to take an input and give an output potentially very quickly and potentially with low energy cost. So that's a pretty active area of research that who knows where it goes, but has potential. And again, looking back at history, you have no idea which technology is going to be the one to really take off. And just the fundamental kind of exploration is what you have to do.
That's quite fascinating. So I kind of want to talk about AGI, artificial general intelligence, and more specifically, how we're kind of leaping towards that, or are we with LLMs? Now, in your opinion, does LLMs getting faster and smarter have any implication towards us even inching towards AGI? Or are we just getting way more sophisticated in a very confined sandbox environment? And having much faster LLMs has no implication that we're even getting incrementally closer to AGI.
In my opinion, it seems to me it's not the right direction towards AGI. It seems like I could imagine it getting arbitrarily close to approximating it. There just seem to be some fundamental differences between at least the way our intelligence works and the way an L.
What would be that threshold of like, hey, this is now we're in the Turing test? Or at what point would you realize this is no longer something that's just learning how to answer, but it's actually somewhat conscious, whatever conscious means?
I feel like one fundamental difference is like the amount of information that it takes to train an LLM versus the amount of information it takes to train child. The child doesn't require being trained on the whole sum of all human written words. And so that seems to speak to
Oh,
really sort of a fundamental difference between what's going on.
that's a very interesting answer. And yes, and we're in a wild world here where we're inching apparently towards AGI. And that estimation of AGI was like 2055, and now we're like in the 2030s. We have blockchain, just a really effective and efficient way to communicate data, store data, process data. And we're moving to the world of quantum computers. We put these three together and we let this process itself out with just a little bit of time. Do you believe that we have any predictive power of what the future might look like, or any sort of prediction at this point is purely fiction?
It's so hard to say. If I said something, I'd be putting myself at grave risk of being proved to look very foolish in the future. It could go in so many directions, and there's so much we don't know. I mean, we don't even really know how quantum mechanics works. We know well enough to build machines that so far have worked the way we thought they would, but there's still mysteries at the heart of it, and who knows how it will play out.
Yeah, let's start there, Jesse. What is your personal philosophical interpretation of quantum mechanics? Are you a Copenhagen
Oh,
kind of person?
I like to defend the many worlds interpretation. I wouldn't say that I would stake my life on it, but I think that it's intriguing to say the least and quite plausible.
Do you have a more nuanced like opinion on what kind of interpretation of many worlds do you subscribe to?
Well, I mean, the way I see it is that the theory of quantum mechanics has two parts. One of them is this relatively simple equation, the Schrodinger equation. It predicts the behavior of waves. Everything is a wave. It tells you what those waves do, just like lots of other kinds of waves we know about. Good. Then there's this other part that's like, oh, but you can't actually see the waves. If you try to measure a wave, you have to do this thing called a measurement, and we don't know what that is really. And when you do a measurement, as Einstein put it, God plays dice with the universe and chooses an outcome of your measurement at random. And somehow doing this measurement causes the state of this wave to suddenly change for no reason at random, instantaneously. And so that second part like doesn't make any sense to me. And so what the many worlds view says that I like is that all you need is that first part, that wave equation. That's all there is. It's that we are also described by that wave equation. And so what would these waves think if they, could think? And that's what we are. So what would you see? What the Schrodinger equation predicts is definitely branching into these different
Mm.
outcomes. And so the question is that enough to explain what we see? Or do you need something else like the collapse that the Copenhagen interpretation predicts or something else? And many worlds idea says, no, maybe all those different things actually just exist. And there are different versions of ourselves. Instead of the measurement showing one outcome, you branch into different parts of the wave function and see the different outcomes in different versions of yourself.
Yeah, so pulling that interpretation and superimposing it on the famous double slit experiment, and I guess the adapted version as well, is the delayed choice quantum eraser. Because I always see it through a Copenhagen perspective of wave function collapse. How would you interpret that, in your opinion, through the lens of many worlds?
Well, see, that's the nice thing is that things like the delayed choice quantum eraser experiment are only confusing if you try to do something like the Copenhagen interpretation. If you look at it in terms of many worlds, it's like there's no mystery because the idea is that um, when the worlds split, they don't completely split. They just become very well separated. And so in principle, they could come back together. And so what happens in like something like a delayed choice quantum eraser experiment is that they'll say, oh, a measurement was performed. Uh, But if it doesn't, when I think about it as separate worlds, if they don't get too separated, then you can undo that separation. That's the erasing part. And so even if you've already done the measurement, as long as you can still in some way undo part of it to erase the information, you can go back and change what you now see as the outcome of the experiment. And
Mm.
so people don't like the many worlds interpretation because it's disturbing if you really think about all the different things that have happened to you in the different worlds. But it seems to me to work well.
Now, taking one more macro perspective here before we zoom in on specifically quantum computers, I kind of wanted to pick your brain on the theory of everything or unification theory. Do you subscribe to that notion that there's this parsimonious reconciliation of everything from general relativity all the way to quantum mechanics? I spoke to the former CTO of NASA the other day, and he was saying that that's an erroneous assumption, that there is a need for the theory of everything. There could be these independent theories at different stages of life. And I don't personally understand that because there has to be some process, there's some gradation of where this uncertain statistical world of quantum mechanics becomes this classical Newtonian world that we experience on the day to day. So I wanted to get your opinion on that.
As I certainly it would be very sad if there weren't
Mm.
one underlying theory. So far, it's worked very well for us in science and in physics to keep finding more and more fundamental theories. There's the gravity that works on Earth, and there's the gravity that works to make the planets go around the sun. And it turned out, oh, it's actually the same thing. And that was an amazing discovery because
Right.
you would not have thought that without Newton's theory of gravity. And then we keep going farther and farther, and things keep getting more and more unified. That leads us to think that there must be one. We can keep going.
It is parsimonious. It's that abstraction, iterative process. Why would you assume that that level doesn't keep happening? There has to be these discrete and separate, discrete and
Yeah, I mean, I would just be so shocked and dismayed if that were the case. It would overturn the way everything really seems to work. We don't know where it all comes from to start with. It would change certainly my outlook if that were the case in a dramatic way, and I would be very surprised.
Yeah. So how do you wrap your head around gravity playing a role in the quantum world?
That's a hard question to answer. In terms of the technology that we're building with quantum mechanics, it's all non-relativistic. So the effects of gravity and even the effects of things like particles and antiparticles, we don't need to deal with. In everyday engineering, you don't have to deal with what happens when you go close to the speed of light, at least for the most part. You have to remember it all does come from this underlying relativistic theory. When thinking about what does it all mean, you do need to remember that at the end of the day, we do have to answer those questions, and everything we do has to be consistent with that. No particular horse in the race, though. I find the idea of emergent space-time very intriguing. Space-time that we see um, is not fundamental, but sort of just
Right.
a convenient way that we observe.
So now pulling towards your day to day here, what would be one of the biggest breakthroughs you would hope for in the realm of quantum mechanics to kind of see the industry push itself forward?
In terms of the technology, I think we need new platforms for quantum computing. This is my opinion. I think that like a lot of the leading things right now, the superconducting qubits, the trapped atom qubits. They're the first, moderate scale demonstration that this stuff actually works. But the first thing that you get to work is not necessarily the thing that is really going to transform the world. So I think it'd be very unwise to stop looking at new platforms. I actually just showed this slide in my class the other day where you can look at sort of going back in time, all the different computing technologies. It goes back a long ways. Before silicon, we had vacuum tubes. Before vacuum tubes, we had electromechanical computers. You can keep going back. You can go back another 100 years. Charles Babbage was making computing devices that were a series of gears that you turn with a crank. And at the time, they thought if we just keep adding more gears, we can build this amazing computer. And they poured money into it. But that was in the end not the way to go. So getting stuff that works at room temperature, solid state devices, that would be.
But isn't that the biggest challenge with quantum computers? That issue of decoherence, and you got to get those electrons stabilized at practically close to 0 Kelvin. And I would imagine like that's one of the biggest issues in the industry is just being able to create the environment where you could do any sort of calculations.
Yes, that's the hard part. And the interesting thing is that this whole issue of decoherence, what it really is entanglement. Like quantum entanglement is this just like the weirdest thing in quantum mechanics, and it's not uncommon at all. In fact, the problem is that it's too common. Like we swim in this like a sea of entanglement. And so what we're able to do with quantum computers is not generate entanglement, but it's to get rid of all the entanglement and then bring it back in only where you want it. And so that's what we're like learning how to do is to harness entanglement. And sort of maybe the easiest way is just to cool something down extremely cold temperatures, or maybe also put it in an extremely high vacuum, things like that. I could see looking back in the future and saying, oh, that's the vacuum tube version. That's the your version of how to harness entanglement. Like maybe we can find more clever ways.
Now, I wanted to get your philosophical perspective on this. Are photons better thought of as messengers for data, used as tools to make actual measurements, or are they active participants in a quantum system?
The obvious use of a photon in as a quantum device is for communication because they travel very fast, speed of light,
Mm.
and they travel long distances without being disturbed by anything.
And they have
so
no
this is
concept
like
of time, which I think is a fascinating idea.
right.
They can travel the entire universe.
Just it would not, see time passing. So in terms of, platforms for quantum technology, it's sort of like a because like it's this issue of controlling entanglement is that in order to not have things become accidentally entangled with other things around, you want your object to not interact with anything around it. You want it to be almost like invisible to everything around it. But at the same time, you want to build a computer out of it or something. And so you have to have the ability to control it, and you have to be able to control it very accurately and very quickly. And you need the different parts of your computer to interact with each other. And so those are two opposite things. You want it to not interact, you want it to interact. And so different possible platforms strike different balances between those two things. And in the case of photons, they interact with each other very weakly. And so in that sense, it's a little bit hard to use them as qubits in a quantum computer, but easier to use them for communication. But like I said, if you're more clever, you can find ways around these things. And so while it's more difficult to get photons to interact with each other and to become entangled with each other, things like that, people have figured out ways to get around that. And so once you can get around that, then you can think about taking advantage of this fact that they're so isolated from their environment that their quantum state, think of it as just the polarization of light, which is kind of a familiar thing. That's really the quantum state of the photon. So I think photons are very promising for both communication and computing.
Yeah. And on quantum entanglement for a moment, as famously Einstein quoted as spooky action across a distance, I always wonder, is this sort of communication transmitting any meaningful data? Like, can we use quantum entanglement to actually send information in a non-local way? Or is it just arbitrary, random pieces of information that we can actually leverage to better human life?
Well, you can't send information faster than the speed of light, distributing entangled particles. That's sort of a thing you can prove. Um, Seems like you could, but what you can send though is a random string of zeros and ones. If you have a bunch of entangled particles and you send one of the members of each entangled pair to one person and another person very far away, and they each perform measurements um, on those particles, what each of them can wind up with is the same random string of numbers. They can get them instantly faster than it would take light to travel between them. So no information, right? It's just random.
Yeah, of like duplicating yourself or teleporting. It's purely fictional in the confines of quantum entanglement.
If you're willing to go slower than the speed of light, then in principle you could teleport. What I was going to say about the random string of numbers is actually that is useful because that's the basis for cryptography. If you can share a
Right.
random key with someone, then you can encode a message that no one else can decrypt. And so that
Right. You can
forms the basis.
establish a handshake across a distance in a non-local fashion, but sending specific strings of data is a little more complicated. Interesting.
Right. And there is also quantum teleportation, which is a thing. It's a very nice name for an experiment they did with photons. And what it does is if you have a photon over here and someone else has a photon over here far away, and this photon is in some quantum state, you can basically copy the quantum state of this photon onto this one, destroying the first one in the process. The idea being that if you have an object, all it is its quantum state. And so if you can recreate that same quantum state somewhere else, that object is now over here. And
Right.
so that it does require communication slower than the speed of light from one to the other. So it doesn't go faster than light, but if you could transport an object uh, at the speed of light or just below it, that's still very fast. And now, okay, don't get too excited because um, this just transfers the quantum state from one place to another. You would still have to physically create the object somewhere else. So the way I think of it, sort of poetically, is like if you wanted to teleport yourself, you'd have to create an identical body of yourself somewhere else, like by some 3D printer or something. Um,
You have to destroy the version of yourself.
yes, you do. So it's sort of like destroying one version of yourself and breathing the spark of life into this other copy, bringing it to life.
Yeah. And that invites a whole slew of philosophical questions of what it means to be you. And if we're going to agree that you've recreated yourself and the new version is technically you, then we run into all sorts of questions of what is it? Again, we for the longest time thought our heart was what made us us. And then the whole argument of a heart transplant kind of was the awkward elephant in the room. And then now we said, no, it's the brain. But if you compartmentalize that, if you were to just damage your prefrontal cortex, would we all agree that you're still you? Most of us would say yes. So at what point do you still become you? Is it just your genetics and your experiences? And if that's the case, then maybe we look at all this as being the biggest constraint to living on. And if you can put all your thoughts into this machine can live on forever and you can talk to it and conversate with it for time and time, then perhaps we're going to all live forever to some extent. It's all a very interesting. And I know it sounds all crazy science fiction, but these things seem very far away until they're at our doorstep.
Exactly. And I'll add that in terms of the question of like, what is the consciousness that you think of as you gets even more interesting if you start thinking about it in the context of the many worlds interpretation, where the being that you think of as you is constantly branching into other versions that you don't perceive.
Is there any way for these universes to communicate in any capacity with one another?
In the sense of, like I was saying, with the delayed choice quantum eraser, if you can if you can do what was done, and then everything's reversible. There's nothing in the equation that says you can't just run everything backwards. The
Right.
difficulty is that once things become so impossibly entangled with each other, it would be very hard to do. It's like saying you stir the milk into the coffee and then you try to stir it the other way and hope that it separates back out. It's probably even less likely than that because of the complexities of quantum entanglement.
Right. So all this crazy, awesome theory, how does this translate to your day to day? Talk to me about some of the companies you're working on.
So in the quantum space, I don't do too much with entrepreneurship or anything. I mean, maybe someday. We've explored a few collaborations with startups and things like that. The technology that I work on actually is based on these defects in diamond. So the material is diamond, and then there are these defects that host electrons, and you can control the quantum state of those electrons. And it turns out this is something that's quite close to commercial application right now, not for computing, but for other applications like making sensors. And so I'm very excited by that because having a near term application that has potential to be commercially viable, I think that's like the foothold that you need to start building up to something bigger and bigger. Something I learned was that the first commercial applications of the transistor were for hearing aids. They were these amplifiers that they had better amplifiers made out of vacuum tubes. And so they could make this very small but kind of crappy amplifier. So what is it good for? Well, you can make a very small amplifier that goes in your ear. And then once it had some application, it starts getting developed more and more and eventually takes over from the vacuum tubes. And so These kinds of things like making better sensors for magnetometers and things like that are one of the focuses of my lab. And then on the music front, I'm looking at how these algorithms can be used different in different aspects of technology and different software applications. Initially, looking at the space of generative music composition, I feel like that in particular now is pretty saturated with AI, and so a little bit crowded. Try to focus in on some of the unique aspects from this physics-based model that might give you some control that just like an LLM-based generative AI kind of thing doesn't allow you to do.
Don't you find it funny if we were to take a machine going back into the past 5, 6 years ago, and you and I were sitting here talking about what would be the first things AI would disrupt? We'd probably all agree it'd be something that's just very scientific, systematic, and patternized, like being a doctor, lawyer, the field of medicine. The things that make us uniquely human is the things that are going to go last. And it's kind of funny to see how AI is truly excelling in the fields of art and music. And it's like we're all super unique, but perhaps we're just a few bytes away from being replaced. And I kind of want to pick your brain on that perspective.
Sort of what I was saying a little bit ago is that like it makes you think like why do we like uh listening to music? Why do we like looking at art? You think, oh well, we like looking at art because it's like a really amazing picture. Like it's somehow uh really cool to look at, really looks realistic or something. And then suddenly AI can make, billions of those. And well, was that even what we wanted in the first place? It forces you to reevaluate what you're doing. And sometimes it is what you want is you just want some cool looking picture. I'll certainly make use of AI for that when I need a cool graphic for something. But I don't necessarily want to go to like a museum and see a bunch of AI generated art.
So Jesse, if music is a phase transition, then a great composer is doing something analogous to what a metallurgist would do when it's designing alloy. How does that change your perspective on how you see music?
Yeah, well, there's all this hidden order. I mean, some are not so hidden, but if you analyze it, then you can sort of really see uh, all the pieces and how they fit together and why. And I mean, I'm not the first person to describe the order that exists in music. That's been the job of music theorists for all of time.
Right.
But most of music theory has been from the top down. Where you look at music and you say, okay, here's how it all fits together. The view that I have now is a bottom up. It's like it emerges, uh, in a way, almost spontaneously. In a way, the composer is like the metallurgist, but in a way, they're like almost part of the system that's giving rise to this emergent structure.
I think a lot of this progress in AI is really making us introspect on what it really means to be human. Because we might think of humans as being at the epitome of the apex of intelligence. We are evolution's grand prize to some extent. But the humbling reality is I might just blow right through human intelligence and not look back. The real threat that AI might pose to us is not that it will be like intrinsically malevolent towards us. It's that we will become entirely obsolete towards it. The same way you would kill a whole colony of bees because they're on a real estate property that you're going to doing a whole new project on, or you'd run over a bunch of ants and wouldn't think twice because they're in the way where you're getting. It really does make us wonder, where did we just get this giant leap from nothing to LLMs, or is this delta, this rate of change, going to continue? Because if we're going to continue accelerating, not even maintaining the velocity we're at, I cannot understand what the future is going to look like.
Yeah. And I mean, it is a little frightening because we don't know. We've definitely gotten to a point in technology where we can destroy ourselves, and we haven't yet. We've come close though, and you hope we can be careful enough.
Right. One of the solutions to the Fermi paradox is a great filter. And the question is whether that goes ahead or behind us. And one of the great filters might be that we are so much more likely to create technology to destroy ourselves before we create that technology to be able to spread out and become interplanetary. Like the threat of a nuclear winter killing us all is going to exist for way too long before we can travel to like Alpha Centauri or some closer star system. If that's the case, it's kind of a little depressing path forward. Yeah, it's it's definitely stuff to think about.
There was a talk in our department the other day, and it was on the topic of Penrose tiles, these aperiodic tilings discovered by Penrose. But it turns out actually it was discovered by an amateur mathematician before Penrose. But the interesting thing was this amateur mathematician had this other theory, which was that the dinosaurs actually went extinct because they had very rapidly achieved human levels of intelligence. Because in the geologic record, the amount of time it takes to go from pre-human apes to humans was a blink of an eye. And so perhaps the dinosaurs achieved sort of a human level intelligence, developed nuclear weapons, and destroyed themselves. And the layer of radioactive material that we attribute to the meteor strike that killed the dinosaurs was actually due to the nuclear Armageddon brought on by the dinosaurs. No one actually believes this is true. This is crazy.
Something comparable to that can equally likely be true. The idea that intelligence is linear as we go through time, as we just get smarter
Mhm.
collectively, is so flawed. You can just look at Gobekli Tepe and you just instantly realize we have no idea what went on just a few thousand years ago. Just look at the pyramids. We have to think of like aliens to just reconcile these. We can't even pick up blocks that big today. So it's just nothing really adds up, to be honest.
Well, again, the thing is that it doesn't take that long for people to develop new technologies. And so the ancient Egyptians were around for a very long time, for civilization for thousands of years. So if you think about how things have changed over the last 100 years in our civilization, the Egyptian civilization was around for long enough to have all sorts of things invented. They weren't stupid. They were just as smart as we are. And they just lived a long time ago. And so to think that, oh, anything they were able to do must be obvious to us, this sort of assumption that everything is linear. And so things can be nonlinear, they can accelerate faster. They can also go back.
Right. It could be like a cyclical pendulum. And just for perspective here, I think that we are closer to the latter part than the Egyptians are to Gobekli Tepe. So there's just none, it's all incredible. And I believe I read somewhere, I can't remember where it was, that if we had done nothing, if we were just ceased to exist today, how long will it take for the ground to just consume everything that gives us an indication that there was human life here? So if you were to look from space in 100 years from now, if we were to just completely disappear, we would look at Earth and we'd be like, oh, I can't really tell if anything ever lived there, right? There's no real trace of human civilization. That's pretty scary because 100 years in perspective is not even a blip in our timeline.
And if some other species came around 65 million years later and dug up our fossils, would they what would they know about us?
So much to think about tonight when I go to sleep. Jesse, it's been such a pleasure talking to you. I know this was supposed to be 20 minutes, but I can do another 4 hours and you're just a ball of endless wisdom. So and I was reading up on your story online and I'm like, this guy is just at a whole other level. So it's been an honest pleasure picking your brain for almost an hour. And how can people get in touch with you if they want to reach out?
Well, I have my website through Case Western Reserve, and I have my own personal website, jesseberezovsky.com, where I have some of my stuff I've worked on. And happy for people to get in touch.
Jesse, it was a pleasure speaking with you. And I look forward to all the great stuff you're going to be doing.
Yeah, thanks. Pleasure speaking with you.